Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper from the Hugging Face trending list, published on December 8, 2025, just yesterday. It shows that large language models can teach themselves to perform genuine parallel reasoning, achieving performance gains of up to 24.5% and inference speedups up to 4.6 times, while maintaining 100% truly parallel execution. The paper is titled, Native Parallel Reasoner: Reasoning in Parallelism via Self-Distilled Reinforcement Learning. And as we will see later, the implications for fast, scalable reasoning models are quite significant. Also, the authors shared a full GitHub repo. You'll find the complete NPR pipeline split into stages for NPR 0, NPR beta, and the RL-trained NPR, with environment setup, dataset prep, and training scripts, plus evaluation code, a small web demo, and utilities to convert and run their release checkpoints. On Hugging Face, you'll find the 4 billion parameter NPR reasoning models, full precision chat weights, plus example code for math and logic problems, with and without explicit chain of thought. Figure 1 tells us that the native parallel reasoner can both think better and think faster than standard sequential decoding on the AIME25 benchmark. The left diagram contrasts a base model using sequential decoding with the native parallel reasoner using self-distillation and the PAPO reinforcement learning stage. The center plots show accuracy rising above prior state-of-the-art, while parallelism climbs to 100%. On the right, the bar chart shows that the 4 billion parameter native parallel reasoner processes tokens at roughly 4.5 times the speed of the sequential baseline. Figure 2 shows how the native parallel reasoner gradually learns to think in parallel rather than being programmed by a teacher. The left block trains NPR 0 with reinforcement learning that rewards following a parallel-friendly format. The middle block uses self-distilled data, which means the model trains on its own best parallel traces to create NPR beta with a special parallel attention mask. The right block then applies parallel-aware reinforcement learning, so the final native parallel reasoner optimizes real branching decisions during inference. Table 1 spells out the exact tag-based script that the model learns to follow for parallel reasoning. The guideline block lists several plan entries, each a one-sentence strategy that defines an independent branch. The following step blocks hold detailed, self-contained analyses for each plan, which can run in parallel. Finally, the takeaway block compares those steps, synthesizes a decision, and ends with a short user-facing summary and boxed answer. Table 2 makes the main performance story concrete, showing that the native parallel reasoner reaches the highest average accuracy across all 8 reasoning benchmarks. The top block compares strong open baselines and multiverse models, which already use parallel-style fine-tuning. The middle block, where the native parallel reasoner row is highlighted, shows clear gains over both sequential and multiverse-style training. The bottom block repeats the comparison when starting from the smaller QN3 base model, and the native parallel reasoner still delivers the best scores, which means the parallel reinforcement learning recipe scales across bases. Alright, 2 takeaways stand out. Large language models can teach themselves to perform true parallel reasoning, and this self-distilled reinforcement learning recipe delivers both higher accuracy and several times faster inference without any external teacher. This points toward more autonomous, scalable reasoning agents. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.